So, today we will discuss the extension of the equation number 1, that is the Fourier law of heat conduction as stated in the previous class to the 3-dimensional system. So, today's class the subject matter is generalized Fourier equation. The subject matter of today's class is generalized Fourier equation. Generalized Fourier equation. Then we must talk with respect to the 3 perpendicular Cartesian coordinate system or the spherical polar coordinate system, that is the r, theta, phi, or the 3 coordinate system as appears in the case of the cylindrical polar coordinate, that is the r, theta, z. So, in the present class we will see the extension of the equation number 1, that is the q by a equal to minus k del by t by del by x to 3-dimensional Cartesian coordinate system. Once we will go through this generalized equation in the 3-dimensional Cartesian coordinate system, it is my request to all of you to go through such equations in the case of the spherical polar and the cylindrical polar coordinate system as well. However, the derivation of this Fourier generalized heat conduction equation in the spherical or polar coordinate system or cylindrical polar coordinate system may not be so much essential, but you must know the format of that equation, because in the coming class we will discuss the radial systems, especially the spherical and cylindrical systems. Then you have to emphasize on the fact that in order to convert this 3-dimensional problem into a single dimension, you have to consider the heat transfer rate along those 2 directions is of such a magnitude that may be neglected due to the infinite dimensions along those directions. That means, if I am talking about the x direction, let us suppose the dimension along the y and z direction is so much infinite that heat transfer along y and z axes may be neglected, and in the case of the spherical polar coordinates only the radial direction is considered and the dimensions of that spherical system along the theta and phi direction is supposed to be infinite, and hence the heat transfer along those directions may be neglected. And similarly, in the case of the cylindrical polar coordinates, the dimensions along the theta and z directions are considered to be of that magnitude. So, let us go through the Cartesian coordinate system. We will derive the generalized equation in the case of Cartesian coordinate system. So, with respect to the equation of continuity that we have gone through in the fluid mechanics course, that is a momentum transfer prior to this midterm examination. Here also we will first consider a volume element. So, 2 dimensions. Let us consider for the derivation purposes today the Cartesian coordinate. So, let us suppose this is your volume element. dimension along these three Cartesian coordinate axes. Let us suppose this is the dimension of this volume element along x direction, delta x, along y direction let it be delta y, and along this z direction let it be delta z. This is z. Now, so the formulation is, let us suppose the rectangular, this is the volume element in this three-dimensional Cartesian coordinate system. Here we have to consider one point, this having the coordinate x, y, z. Similarly, another consider this point Q, its coordinate should be x plus delta x, y plus delta y, z plus delta z. Okay. Is the meeting point of three faces, this face, and this face. Is equivalent to the meeting point of all the faces through which heat energy is being received in x, y, and z directions. Visualize. This is the surface through which the heat energy entering the volume element around the surface. Right? This is the surface through which the heat energy is being received by this volume element around this x-axis, and this is the surface behind the plane of the blackboard. This is the surface through which heat energy is consumed. Right? Similarly, the Q, x plus delta x, y plus delta y, z plus delta z. The meeting point of all these faces, through which volume element releases the heat energy along x, y, and z directions. Okay. This is the formulation of the problem, that considered a volume element having the dimensions delta x, delta y, delta z as the coterminous dimensions along the x, y, and z axes respectively. X, Y, Z is the meeting point of all the faces through which heat is being received by the volume element. Another point is this volume element, that is Qx plus delta x, y plus delta y, and z plus delta z is the meeting point of all these faces of the volume element through which this this energy is being receded or being transferred from this volume element to the assumption which is required here, or the derivation of this three-dimensional heat conduction equation assumption is heat is the only form of energy. Heat is the only form of energy being exchanged by the present volume element. So this is our formulation, that this is the volume element considered in the direction of the flow of the heat energy. Another, we have described the nature of the points P, X, Y and X, Y, Z, and the Q, X plus delta X, Y plus delta Y, Z plus delta Z. Another assumption that we have made, the heat is the only form of energy being exchanged by this present volume element. This is the assumption that we have. That means we need not to consider the transformation of heat energy into the work or vice versa. So there is no need to utilize the principle of thermodynamics here. The only thing we should utilize here is the conservation of energy, that the entire energy will get conserved during the present formulation. So let us keep the diagram and proceed further in this direction of the deriving the three-dimensional fluid heat conduction in Cartesian coordinates. So let us come to the principle now. Principle. If any physical process or chemical reaction is taking place inside the volume element, leading to heat evolution or generation. That means, let us suppose an exothermic reaction is going on inside the volume element, or you are rubbing the two hands together to generate heat energy. These are the examples of the chemical reaction or physical process which may lead to the evolution of heat. So leading to heat evolution of generation. Then principle of conservation of energy. For the present case can be given as rate of heat flow into the volume element minus rate of heat flow out from the volume element that should be equal to how much? The rate of change of energy of the volume element, that should be equal to rate of change of heat in the volume element minus rate of energy production inside the volume element due to the reaction. Let us see number 1. This is the basic principle which is involved in the derivation of the three-dimensional Cartesian coordinate system Fourier equation. Now let now the only half of the blackboard will be removed, and every time this will be considered as a reference. Now let qx is equal to amount of heat energy flowing in or flowing out the volume element along the x direction per unit time, and let us suppose qy and qz is the amount of heat energy flowing in or flowing out the volume element along the y and z directions respectively per unit time, that is along the y and z directions respectively per unit time. So now you can write if the quantity qx, that is the amount of heat energy entering the volume element per unit time along the x direction. If I am considering this direction, that is x direction, that means this will be the area through which the heat energy is being received, this area. So the qx, that can be written as minus component of the thermal conductivity along the x direction kx, and what is the area perpendicular to the x axis, that is delta y into delta z. So kx into area, that is the delta y delta z into the temperature gradient, normal temperature gradient delta T by delta x at x is equal to x. Let it be question number 2. Similarly, qy is equal to minus ky delta x delta z deva t by deva y at the value y equal to y. Similarly, qz is equal to minus kz delta x delta y deva t by deva z, value at z equal to z. Let it be question number 3. Let it be question number 4. Similarly, heat energy which is being receded by the volume element along the x direction, that can be abbreviated as Qx plus delta x, that can be given as minus Kx, other quantity will be remain similar, Kx delta y delta z, but the temperature gradient needs to be considered delta T by delta x as a point x equal to x plus delta x. Let us see question number 5. Similarly, Q y plus delta y, that is equal to minus Ky delta x delta z, deva T by deva y, the value at y plus delta y. Let it be question number 6. Similarly, Q z plus delta z, that is equal to minus Kz delta x delta y, the temperature gradient along the z direction at the point z equal to z plus delta z. Let it be question number 7. So, the value of each and every quantity flowing in and flowing out along the three mutually perpendicular Cartesian axes x, y, and z can be represented in this manner. So, all the quantities which have been included in the first two parentheses of the equation number 1 will be completed right now. Now, let us try to arrive at the quantity which is there in the right hand side of the equation number 1 in each parenthesis. So, here you can write here Kx, Ky, Kz are the components of K along x, y, z axes. Question number 2, 3, 4, that is the equation corresponding to heat flowing in, where the equation number 5, 6 and 7, that is equivalent to the heat flowing out from the volume element. Volume element. Now, amount of heat retained in the volume element. Now, amount of heat retained the volume element, that should be equal to how much? If delta Q is the time heat energy which is representative of the heat retained in the volume element, that is the per unit time, that is the delta Q by delta T into delta x, delta y, delta z, that is multiplying by the volume of the volume element. So, let it be question number 8. If Cp and rho are the specific heat capacity at constant pressure and density of the material of the volume element, then quantity delta Q by delta T can be represented as Cp into rho into the change of temperature of the volume element per unit time. Cp into rho into delta delta T y upon delta T, that is the mass into specific heat. You can consider the unit volume, and then Cp, that is the specific heat capacity, into the mass, that is the 1 into density, that is the mass, into change in temperature per unit time. So let it be question number 9, and let QR is the amount of heat produced due to the reaction per unit time number 1. Putting equations 2 to 10 in one, we get putting all the equations ranging from equation number 2 to 10 in the equation number 1, that is equation number 1, which stands for the principle of conservation of energy. So right now minus kx into delta y delta z equal to x. This is along the x axis, this is along the y axis, minus kz delta x delta y delta t by delta z at z minus heat energy out, so minus plus, so this will get plus kx delta y delta z delta t by delta x at the value x equal to delta x plus ay delta x delta z y at the value y equal to y plus delta y plus kz delta x delta y and the value of this temperature gradient at the point z equal to y plus delta z. That should be equal to rate of change of heat in the volume element, that should be equal to rho Cp this, that stands for delta q by delta t into delta x delta y delta z minus y, right. So dividing the whole expression, or you can say move one step forward, kx delta y delta z plus this, that should be equal to rho Cp delta t by delta t delta x delta y delta z minus qr. So the dividing the whole expression by delta x delta y delta z, you can write, or you can write kx divided by delta x this plus quantity kz by delta z, the gradient difference in the gradient along the z direction at 2 points, that should be equal to rho Cp delta t by small t minus qr divided by delta x delta y. Now assuming this quantity qr by delta x delta y delta z is equal to sigma, let qr divided by delta x delta y delta z, that is equal to sigma, due to the reaction per unit volume, that is equal to sigma, and taking the limits delta x tends to 0, delta y tends to 0, delta z tends to 0, we can write this quantity kx and this quantity delta x tends to 0, function x plus delta x minus function x divided by delta x, that is equal to x. So this quantity plus deva by deva y deva t by deva y plus kz deva by deva z deva t by deva z, that should be equal to this quantity rho Cp minus small. Now we can remove this portion. Or write kx d2t upon dx2 plus ky d2t upon dy2 plus kz d2t upon dz2 plus sigma equal to rho Cp deva t upon deva t. Isotropic nature of the material of the volume body, assuming the isotropy of the material of the volume body, element, that is kx, that is equal to ky, that should be equal to kz equal to all equal to k let. So let it be equation number 11. So the equation number 11, now this takes the shape k d2t upon dx2 plus deva 2t upon deva y2 plus deva 2t upon deva z2, that should be equal to plus sigma, that should be equal to rho Cp deva t upon deva t. Or we can write starting from the last so we can say, we can write k upon rho Cp sigma by rho Cp, that should be equal to d by small t. Now let us consider a parameter. Consider an operator. Consider an operator from vector calculus. From vector calculus, the parameter is del parameter. This is defined as I dy by dy x plus j dy by dy y plus k dy upon dy z. Square. So del square is equal to del dot del. That should be equal to I dy by dy x plus j dy by dy y plus k dy upon dy z. That should into dot product of same quantity I dy by dy x j dy by dy y plus k dy by dy z. That will be equal to this plus this quantity. So this equation can be written as K upon rho Cp. Right here del square t, that is equal to dy by t by dy x2 dy by 2t by dy y2 plus dy by 2t by dy z2 k by rho Cp into del square t plus sigma by rho Cp, that is equal to dy by t upon dy by t. Or we can write the Fourier equation in the Cartesian coordinate system, dy by t by dy by small t, that should be equal to alpha del square t plus sigma by rho Cp. This is the generalized heat conduction equation in the 3 dimensions. Fourier conduction, generalized Fourier heat conduction equation in the 3 dimensions. Alpha is the diffusivity, alpha is the thermal diffusivity, equal to K upon rho Cp. Let us so the equation number 12 is the generalized Fourier heat conduction equation. Heat conduction equation in 3-dimensional Cartesian coordinate system. Cartesian coordinate discuss the special cases prevailing in the case number 12. Special cases. Number one, no process or no chemical reaction is going on inside the volume element. no physical process or chemical reaction is there in the volume element. It means the value of sigma equal to 0. So, equation 12 takes the shape. Here it will be useful to write this equation, that is equation number 12, as for discussing the special cases. So, equation number 12 has take the shape as alpha del square t, that is equal to d by t upon d by t. Equation number 13. Number 2. If heat flow takes place in a steady manner, if this is the condition which has been imposed along with the condition number 1, that is no physical process or no chemical reaction is going on inside the volume element. And secondly, if you are imposing the second condition that the heat conduction is taking place in steady state, that means there is no variation of temperature that is taking place with respect to time. That means it implies this quantity d by t upon d by small t, that should be equal to 0, implies that alpha del square t is equal to 0. Now, since the thermal diffusivity of the material can never be equal to 0, so del square t is equal to 0, and this is the Fourier equation in the steady state. Del square t is equal to 0. Extending this equation to 3-dimensional case. Extending this equation, we can write d by 2x by d by y2 plus d by 2y, d by 2t by d by y2 plus d by 2t by d by z2, that is equal to 0. This is your steady state Fourier heat conduction equation in 3 dimensions. So, if only two directions such as x and y are only considered, then the shape of the equation is d by 2t upon d by x2 plus d by 2t upon d by y2, that is equal to 0. This equation is well known, the Laplace equation of heat conduction in 2-dimensional cases. This equation is of immense importance so far as the numerical evaluation in a 2-dimensional plate, numerical evaluation of the temperature at a particular coordinate in a 2-dimensional plate is concerned. This equation is utilized along with the utilization of the finite difference techniques to develop the nodal equation for each and every node available in that particular 2-dimensional body. The solution of those equations in terms of the temperature of the various nodes T1, T2, T3, T4, T5, etc. You can solve those equations by the Gaussian elimination method, and you can also utilize the matrix formulation method. X is equal to inverse of matrix to the temperature. So, you can determine the temperature at the various nodes, that is the temperature at the various position in a 2-dimensional plate. So, this equation is called the well known Laplace equation of heat conduction. Laplace equation of heat conduction in 2 dimensions. So, I am going to suggest you that this is the description of the generalized Fourier equation in 3 dimensional Cartesian coordinate system. So, please first have an idea about the generalized Fourier conduction equation. Generalized Fourier heat conduction equation in spherical polar coordinate system. Spherical polar coordinate statement actually you should know. Spherical polar coordinate system, that is r, theta, phi, and the cylindrical polar coordinate system. Cylindrical polar coordinate system, that is abbreviated as r, theta, z. Please go through the statement generalized Fourier heat conduction equation along these 2 system of representation of the Cartesian coordinate data. Thank you.